So we have a 2D motion problem here. A marble rolls across a 0.9 meter tall table at a velocity of 0.39 meters per second. How far from the base of the table does the marble land? The first thing to do here is to draw a sketch. Okay, so we have our tabletop, we have our marble, we have the ground, and then we have the height of the table from the ground. That's 0.9 meters. Okay. And we have this initial velocity of 0.39 meters per second to the right. What's the trajectory of this marble as it leaves the table? If you imagine, it's going to look something like this. Right? We're going to have a parabolic trajectory, sort of semi-parabolic trajectory like that. And the displacement in the x is what we're looking for. From here to there. Okay? So, let's use grasp to solve for this displacement x. Because we're asked how far from the base of the table does the marble land. Okay, so G, what are our givens? For 2D motion problems, let's break it into x and y. In the x direction, we have this initial velocity in the x direction because the marble leaves horizontally. And my question for you is the velocity in the x direction increasing or decreasing? Is it changing? It's not, because there's no acceleration in the x and y. Okay, so Vx is equal to 0.39 meters per second to the right. Do we have anything else in the x? It doesn't look like it. What about y? Well, think about this. In the initial instant, the instant the marble leaves this table, there is no y1 velocity, v1y. The reason for that is because it's the instant right after. It's only the time after that initial instant that the acceleration increases the velocity in the y direction. But the moment it leaves the table, there is no velocity in the y direction. Okay. What about acceleration? Yeah, we're on Earth. At least we can assume so safely. So acceleration is going to be 9.80 meters per second squared down. What about the displacement in the y? Well, we also have that. It's going to displace 0.9 meters. Okay. That's going to be down. Okay, now let's look at the time. Something interesting is going on with time here. The time in the x direction is going to match up with the time in the y direction. That's the critical piece of information that we need to infer. Again, the time this ball travels in the x direction is the same time this marble travels in the y direction. In other words, if I can use this information in the y component to solve for time, I can use that exact same time in the x and solve for displacement. So what are the required information? We need time. We also need the displacement in the x direction alternately. Okay, let's look at the equations that we're going to need here. So we have in the x component, we have displacement x equals velocity x times time. And in the y, we have one kinematic equation in particular that has all these variables as well as time. Can you recall that one? It's displacement y equals initial velocity y times time plus acceleration times time squared over 2. Yeah? Okay. Now, notice this v1y is 0, so that kind of simplifies our work. So that leaves us with displacement y equals acceleration t squared over 2. We're going to isolate this to solve for time. That's what we want. So I'm going to multiply by 2 and divide by a on this side. And I'm going to do the same thing on this side. What does that leave me with? That leaves me with 2 delta y over a equals delta t squared. I can take the square root on both sides. Okay, so that's going to leave me with 2 roots 2 dy over a, equals time. Okay, now we can substitute our givens. We're going to start over here. S. Okay, so what are our variables here? So again, root of 2 times displacement in the y. Oh, sorry, I'm missing a y here. Displacement in the y was 0.9, and acceleration we know is 9.80 equals delta time. I could put this in my calculator. So root 2 times 0.9, brackets closed, over 9.80. That gives me 0.429. Oh, let's go to 4 decimal places. 0.4286 seconds equals time. What do we do with this time? Remember what I said? We can take this time. The time the marble travels in the x is the same time it travels in the y. So we can substitute this time into this equation. So displacement x equals velocity in the x, which we know, 0.39 meters per second, times the time, 0.4286. We solve for displacement x. Let's see what we get here. 0.39 times 0.4286. I get 0.1672 meters. Okay, now let's look at significant digits. We have this number here, which was from the equation, if you remember. It was this 2 here. So that has infinite significant digits. 0.9 has 1 significant digit. 9.80 has 3 significant digits. So we're looking for 1. We're going to take it to 1 significant digit to here. And then we multiplied that by the displacement. This number here has 2 significant digits. This one here had the 1 carried over from time. That's 1 significant digit. So we're going to take 1 significant digit. So we can round this to 0.2 meters to the right. Okay, and then we can paraphrase. The marble lands 0.2 meters to the right of the table. All right, thank you for listening.